Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 17.3. And so in this section, we're going to be learning about the integration property for the Laplace transform. So this is where we start getting into the fun stuff. The real advanced integration techniques comes here, where we have a Laplace transform of f of t divided by t. From the previous section, we learned about how to compute the Laplace transform of t times f of t. Now it's f of t divided by t. So, what is the Laplace formula for this one? So for this one, this is equal to the integral of s equals to a to infinity. So you're technically integrating the Laplace transform of f of t according to ds. So this is technically what we have is, instead of deriving, we now integrate our f of s ds. Okay? And some of you probably already see how this works as a mechanism, right? If our f of s is equal to the integral of from 0 to infinity of e to the negative st f of t, right, dt, how do we get f of t over t? Like, how do we get this t to be divided? Is we integrate respecting to s. How are we doing that? So we want to integrate e to the negative st. We're just going to only focus on this because we are integrating with respect to ds. And so, of course, when we integrate this, we get negative 1 over t e to the negative st. Okay? Cool. But what do we put up for our bounds? Right? Our goal is that we want it to be like this. We want e to the negative st by itself and f of t divided by t dt, right? So we just want this and this by itself. But how do we achieve that? What we do is, first we let this to be infinity so that everything equals to 0, and then to still maintain our s here, we just let this interval be s. That's where that s equals a comes from, because we still want to maintain our s, our Laplace formula, okay? Our Laplace transform, technically. So again, remember that we are integrating respect to s. So these bounds are plugging into s here, not t, s. So that's how this integral comes from. We have the bounds infinity, s equals to a. We are integrating f of s ds. That's what this is. That's where this formula comes from. Okay? So that is this formula right here. This Laplace, the Laplace of f of t over t, is equal to the integral of the Laplace from s to infinity. Okay? All right. Now let's go ahead and apply that. So we have this famous integral here. I'm pretty sure you've seen this integral before somewhere in Integration B. And this does occur. This does pop up a lot. So usually, well, regularly what people would do is they would complexify it and use Fulani, or they would use Feynman technique, which is a little nasty, not gonna lie. I would definitely not use Feynman technique unless you like to just show it off and, you know, if you really love Feynman technique. But the fastest way is to use Laplace. So what we have here is we have the Laplace of sine of 3x over x, where s is equal to 2. So what this means is that we want to integrate from 2 to infinity And then we just take the Laplace of sine 3x, which we know is what? Sine. It's like a constant. So it would be 3 x squared plus 9 dx, right? And so now we just simply integrate this. This is just what? For some reason I don't know how to integrate. 3 1/3 inverse tangent of x over 3 from 2 to infinity. And now what I have, this is equal to pi over 2 minus inverse tangent of 2/3. Technically, with trig identity, the answer is simply 3/2. Okay, you can leave your answer like this, but this is just a simplified version. I just use a trig identity, you know, the reciprocal equals to pi over 2. So, but yeah, this is our answer technically. Inverse tangent of 3 over 2. And look how fast that was, right? Again, Laplace is super fast for ugly integrals. Here, you know, I don't have to use Feynman technique and take the long way route, whatever. Laplace is just straightforward. Okay, let's do another example. Okay, so we have an awkward looking integral here. Can we use Laplace on this? Yes, we can. We can use Laplace on this. We technically have from 1 to infinity, and then we have the Laplace of pretty much 1 minus cosine of x dx. So now the Laplace of this, 1 to infinity, and so now this is what? 1 would be like 1 over s, so it'll be like 1 over x minus this, the Laplace of cosine is x over x squared plus 1 dx. And so now we simply have ln of x minus the ln, the half of ln of x squared plus 1 from infinity to 1. Okay, plug in 1, it's, you know, 0, minus half of ln of 2. So, what, let's see. The limit as x goes to infinity, we technically have x over the square root of x squared. Oh yeah, it's going to go to 0. That's going to go to 0, because ln of 1 is equal to 0. Okay. So, technically in this case, our answer would just simply be a half of ln of 2. And that's our answer. See? Again, very quickly, super fast. That's all we got to do. Okay? All right. Next integral. Sine of ln of x over ln of x. Interesting. Well, because there's ln of x's, let's let u equal ln of x to see where this goes. Let's see, if we, 0 is going to give us negative infinity. ln of 1 is 0. We get sine of u of over u, then e to the u. Okay. Close, but not quite. However, you know, there's one simple thing that we can do to turn this into a Laplace integral, and that's literally letting u equal negative x. And so now this is just simply the same thing as from 0 to infinity of sine of u over u e to the negative u. Now, this is simply a Laplace of sine of u over u. So this is using the Laplace integration property. Our s is technically 1. So from 1 to infinity, we have the Laplace of sine of u, which is, I'm just going to turn it back to dx. This is, the Laplace of sine is x squared plus 1. 1 over x squared plus 1. And now this is simply inverse tangent pi over 2 minus pi over 4. The answer, simply pi over 4. Okay? Again, very fast. You know, it's just, why use Feynman technique? I mean, it's a beautiful technique, I guess, but it's just a lot quicker to just use Laplace. Okay? So this is our last integral for this section, and we have a very daunting integral. What do we do? Well, first off, we see 1 over x's, so let's just kind of substitute that just to get it out of our way. So we technically have e to the negative u minus e to the negative u cosine of u over u squared du. Okay, so what we have is we technically have a Laplace of 1 minus cosine of u over u squared. Interesting. What do we do with the u squared at the bottom? So, I mean, if we apply the integration property, we technically have from 1 to infinity the Laplace of 1 minus cosine of u over u. Wait a minute. Didn't we do this Laplace transform before? Yes, we have, haven't we? Right? It was something to do with the ln, you know, the ln of s, whatever. If you don't remember, it's okay. We'll color this yellow. Okay. This is technically the integral from s to infinity, and we had 1 over s minus I'm sorry, it was s over s squared plus 1, right? And we had ln of s minus ln, what was a half of ln of s squared plus 1. Okay? And then of course plugging in infinity, plugging in s, we get this. Alright, so what we have is we technically have from 1 to infinity, we have ln of s minus a half of ln of s squared plus 1 ds. So this is our integral. Holy smokes. Alright. Well, let's go at it then, shall we? So I already know, well, if you've, been through this series, the integral of ln of s is simply s ln of s minus s, right? Here, we're going to have to do integration by parts manually because we're not too known about that integral. I'm going to color this. Okay. I'm going to put the half aside, and we have ln of s squared plus 1. If we do integration by parts, we get s 2s s squared plus 1 minus, and then with s here. And so what happens is we actually get, let's say this is minus, so we get minus 1/2 of, and then we have s ln s squared plus 1, and then minus 2 of, well, we have s squared plus 1, so it'd be 1 minus 1 plus s squared, 1 over 1 plus s squared. So that's what it would actually look like, right? Using zero substitution, because we've dealt with this integral so many times before. I'm just double checking, make sure I did that correctly. Okay, so we have minus 2s plus 2 inverse tangent of s. Okay, all of that parentheses. Holy goodness. And now we have to plug in from infinity to 1. Oh boy. We're almost there. It's okay. We're almost there. Let me just lift this up. Okay. So, oh god. Jesus. I'm just hoping I do this correctly. So that's an s. So this is going to be the half. It's going to become positive s. So what you can see is this negative s, that's 2s. It's going to cancel out. Alright, cool. So what we have left, if we simplify this, we have s ln of s, okay, and then we have minus s of ln of square root of s squared plus 1. I'm just going to write it like that, just to easily see, and then plus, oh, well, technically minus, this is minus inverse tangent of s. Okay, now, here's the most annoying part, is doing the limit. The limit, as x goes to infinity, we have x ln of x over x squared plus 1. This is technically infinity times 0, which means that we have to use L'Hopital's rule. So, if we use L'Hopital's rule, I'm just going to separate it like this. 1 over x. This is now 1 over x minus a half of 2x of x squared plus 1, negative 1 over x squared. This 2 gets cancelled out. Okay, so now this is the limit as x goes to infinity. This is, let's see, if I multiply negative x squared, I get, oh, that's not good. I get x, I end up with x cubed. X cubed of x squared plus 1. X cubed over x squared plus 1. And then minus, and then x squared x. Oh, I'm dumb. No, it's not infinity. It's not infinity. Be very careful. Don't let this get to you. This I was hallucinated. I was hallucinating. That's the dangers of computing limits is that you can easily be hallucinated. Okay, so this is minus x cubed and then minus x, technically, right? Because if you multiply x squared plus 1 top and bottom. And now, what we have here is this cancels out. And so now what this actually does equal to 0. So this limit does indeed equal to 0. Okay, this limit equals to 0, does not equal to infinity. Be very careful. Okay, so now that we know that, so this whole portion, so when we plug in infinity, so that whole portion equals to 0. So that means that with inverse tangent, plugging in infinity, we get negative pi over 2. And then minus, and then plug in 1. Let's say that's 0. If I plug in 1 here, I get minus ln of the square root of 2, and then minus inverse tangent of 1, which is pi over 4. Okay, so what we have here is this pi over 4 minus pi over 2. So our answer would be a half of ln of 2 minus pi over 4. Okay. Holy hell, well there you go. Okay, so definitely practice on that so that you can remember the integration property Laplace formula, as well as learning to apply it within these integrals. Okay, so definitely rewatch and try these integrals on your own. Alright, I hope that was helpful, and yeah, thank you so much for watching. I'll see you guys in the next part.